Assalamualaikum and hi everyone. The topic is accelerometer. Accelerometer is used to measure acceleration, velocity and displacement. It also able to measure vibration and shock. The principle behind accelerometer is based on the properties of rotating mass and also Newton and Hooke law. So the first one is for the application in aircraft and satellite, while most of the industrial application use Newton and Hooke laws. This is the basic spring mass system accelerometer. Here we can see the design is using spring mass system and put onto a base. X naught here is the initial position when there is no acceleration. When there is acceleration felt by the base, it will cause the mass to also move on the base and extend the spring. Therefore, delta X is measured as a displacement of the mass. By measuring delta X, we will be able to calculate acceleration by multiplying it with K over M. In the case where mass is decelerates, the same principle applied, except the spring is compressed. The spring mass principle applies to many common accelerometer design. Function of mass will convert the acceleration to spring displacement and is known as test mass or seismic mass. Since accelerometer is a second-order transducer, therefore we need to consider the natural frequency and damping when using accelerometer. The natural frequency can be calculated using this equation here, where it depends on the value of K and M. The characteristic of natural frequency is that the mass will exhibit oscillations when the frequency is the same as natural frequency. The oscillation occur and only friction will be able to bring the mass to rest. So the friction is considered as a damping coefficient. In general, the effect of oscillation is called transient response, and the transient response is described by this equation here, where xt is the position of the mass, S naught is the peak position, alpha is the damping coefficient, and Fn is the natural frequency. So this is the transient response for a mass with damping when impulse input is applied. The point here is x naught, the maximum amplitude. The exponential amplitude decay is described by exponential negative alpha t, and the periodic oscillation is described by sine 2n fn t. The accelerometer can use to measure vibration. The spring mass accelerometer can be used to measure vibration. So the vibration is given by this equation here, and we can put the same equation into the equation of spring mass accelerometer. So from this equation, we get delta X is equal to M over K X naught omega squared sine omega t, where X naught is the peak amplitude of the table vibration. Delta X is the vibration of seismic mass within the accelerometer. This diagram illustrates the spring mass accelerometer on a vibration table. So the vibration table here is vibrate with the amplitude of the maximum amplitude of x naught. The vibration will cause the seismic mass in the accelerometer to displace by delta x. Delta x can be calculated using the equation m over k x naught omega square sine omega t. M over k here is the design parameter for the accelerometer. X naught is the maximum amplitude of the vibration. And omega here is the frequency. Since x0 is also fixed, meaning that the vibration must has a fixed maximum vibration amplitude, therefore the changing variable is omega square. So when we plot the displacement of seismic mass versus frequency, this line here is using the equation that we derived just now. We can see that the displacement of seismic mass is increasing with the value of omega square. However, this result does not explain the real behavior of vibration. In natural vibration, there is a peak here due to the natural frequency. This behavior is not captured in this equation. At natural frequency, the seismic mass is predicted to have a resonant behavior at natural frequency here. Therefore, in order to avoid that, we design a stopper such that it will limit the movement of the seismic mass so that the accelerometer is not damaged during resonance. So by putting the stopper, we can see that the displacement of the seismic mass is limited by the stopper here. For frequency above natural frequency, the motion of mass is proportional to the table peak motion, which is x0, but not to the frequency, meaning frequency does not have an effect on the displacement of the seismic mass when the frequency is higher than natural frequency. When the frequency is lower than natural frequency, it follows the equation. Generally, we want to avoid this region due to resonance that will occur around natural frequency. As a rule of thumb, we consider f must be lower than fn over 2.5 or f must be bigger than 2.5 frequent natural. So in between this region, we want to avoid to operate between this region. For the frequency lower than natural frequency, it will behave follow the equation, meaning it will increase with omega square. But for a frequency that higher than natural frequency, at this region here, frequency does not give an effect on the displacement of the seismic mass, but now it's depend on the x0, which is the maximum amplitude of the vibration. Let's look onto this simple example. We have an accelerometer that has a seismic mass of 0.05 kg and a spring constant of 3 kN per meter. Maximum mass displacement is plus minus 0.02 mm before mass hit a stopper. Determine the maximum measurable acceleration in gravity and also the natural frequency of the accelerometer. So to calculate the acceleration, we have the equation of A equal to km delta x, and all the value are given. K is 3 kN per meter, mass is 0.05 kg, multiply with the maximum displacement 0.02, which gives us 1200 meter per second square. If the acceleration is considered in g, so we convert meter per second square to the gravity, which get 122 g. The natural frequency can be calculated using this equation, where it depends on the value of k and m. So putting the value of k and m into the equation, we get the natural frequency of this accelerometer is 39 Hz. So we have to make sure that the system does not operate around 39 Hz in order to avoid damage to our accelerometer. There are a few more types of accelerometer. that does not use the concept of spring mass system. Okay, we have liquid level accelerometer. The concept of a liquid level accelerometer is that we place a liquid in a U-tube, then we measure the displacement difference when the liquid in the tube is subjected to an acceleration. Under an acceleration in x direction, the liquid in U-tube will move up and down, and the difference of height from rest can be used to calculate the applied acceleration. Next is force rebalance accelerometer. So force rebalance accelerometer use a mass that connected to a spring and damper. When an acceleration is applied, the mass is also displaced. By measuring the displacement of the mass and the value of K and D, we'll be able to calculate the acceleration. Normally, these accelerometers are mainly used to measure rocket launches and other high gravity acceleration applications. The variety of accelerometer is due to the different application with different range, natural frequency, and damping. Most accelerometer give a specification sheet that tell us about natural frequency, damping coefficient, and also a scale factor that relates output to the input. There is also a potentiometric accelerometer, which is the simplest accelerometer. The concept is to measure the seismic mass motion. This is done by attaching the spring mass to the wiper arm of a potentiometer. Therefore, the movement of seismic mass will be changed to the resistance value. This kind of accelerometer has a natural frequency around 30 Hz and limited to steady-state acceleration or low-frequency vibration measurement. The system also need a signal conditioner that able to convert resistance variation to voltage. Second is a LVDT acceleration concept. In this design, the LVDT core is considered as seismic mass. Therefore, the displacement of the core is directly converted into linear proportional AC voltage. This kind of accelerometer has a natural frequency less than 80 Hz and commonly used for steady state and low frequency vibration. The third one is variable reluctance accelerometer. So here the inductive principle is employed. Again, the seismic mass is usually a permanent magnet. When the magnetic mass moves due to the acceleration, the voltage will induce in a surrounding coil. So this kind of accelerometer is used for vibration and shock study. It only produces an output when there is a motion of mass. The natural frequency is less than 100 Hz. The application is commonly in oil exploration to pick up vibration reflected from ground rock strata or called geophone. Next is piezoelectric accelerometer. This accelerometer employ the concept of piezoelectric, where in this piezoelectric material, the voltage is generated when it's stressed. So we can see here that the crystal is attached to a seismic mass. This is seismic mass. So when exposed to an acceleration, the crystal will be stressed by a force of F equal to ma due to the acceleration multiplied with the mass of the seismic mass. So it will produce force that acting onto the crystal. A measure of voltage, meaning representing the acceleration. The output level of this accelerometer is typically in millivolt range, and the natural frequency is higher, exceeding 5 kilohertz, and used for vibration and shock. So this is the piezoelectric accelerometer, where it shows the housing. So in the housing there is a mass and also a crystal. When the piezoelectric crystal is stressed due to the acceleration force, it will produce an electrical output proportional to the acceleration.